Test tomorrow over chapters 3 and 4. So let's very quickly go over our homework and then we will dive into our test review, though understand that the homework problems are similar to problems that will be on the test. Okay, so as we're going over the homework, we are reviewing for the test. We will do a couple more problems like these homework problems at the end of the review, time permitting. And so this hopefully won't be the only review we get over this, since we didn't get as far yesterday as I would have liked. I would have liked a little more practice yesterday also. So books open to page 82. Yes, ma'am.
You're going to record a video for it.
Well, hopefully we're going to get all the review done today. So whatever we don't get done in this video, I may record an extra one, but the hope is to do everything in the next 40 minutes. We'll see if we can pull it off. All right, so books open to page 82. Have your homework out and take a look at problem 28. You did 28 and 29. Read number 28 through part A for us, if you would, Grace. Nice and loud.
As the final step in copper refining, molten copper 1 sulfide and copper 1 oxide are heated to react, producing molten copper metal and sulfur dioxide gas.
And then they give you the formula, and then it asks.
The A, B, C.
Yep, part A.
Part A, how many moles of each reactant are needed to produce exactly 5 moles of copper? B, if there are 5.6 moles copper sulfide and 9.8 moles of copper dioxide, what is the limiting reactant? C, in part B, how many moles of copper will be produced?
All right, and Abigail is not liking the fact that I took her desk out from under her feet there, so welcome to the front row. All right, let's take a look at this. The first question is, how many moles of each reactant, that's these two, remember, are needed to produce exactly 5 moles of copper? Well, remember, the key here is if you know how many moles for just one of them, you're going to divide by the number, the coefficient, to get what the key number is, as I like to call it. So if there's 5 moles, but it's 6 Cu, what is the key number, class? Calculators, let's go. If we have 5 moles that we need, but the coefficient is a 6, what's the key number we're going to use in the problem? 0.833333, right? It's just a whole bunch of 3s. I'm going to write about 3 of them, and we'll call that good. Okay? Take the 5 moles we have, divide by the coefficient. That's going to tell us our key number. But then it says, how many moles of each of these reactants do we need? What do we do with the key number once we've found it, class? Multiply by the coefficient. So 1 times 0.83333, class? You can do that without a calculator. And what about for the next one, the carbon oxide? 1.666. And we'll round to a 1.667 there, moles. So the first question asks, how many moles of the reactants are needed to produce 5 moles of copper? We need 0.8333 moles of copper sulfide, and you need 1.667 moles of copper oxide. Copper monoxide, I guess we should say. All right? Copper oxide. Questions on that? Yes, ma'am.
So for that one, you're only going to be looking at your the ones on the left and nothing on the right?
Because it only asked about reactants.
Okay.
Right? If it had mentioned how much product, how many moles of sulfur dioxide are produced, well, it would be 1 times that 0.833 moles of that as well. It just didn't ask about that. Great question. Good. Does that make sense? Take the number of moles, divide by the coefficient. That's your key number, and that's what you would multiply by if it had asked every coefficient. It just didn't ask about sulfur dioxide because that was a product, not a reactant. Questions on part A? Part B changes gears here. So all of this information is totally worthless to us now because they totally changed the problem on us. Part B, it asks, what if we have 5.6 moles of this? What if we have 9.8 moles of that? Which one is the limiting reactant? Well, if you have multiple moles, then you're also going to get in class multiple key numbers. And whichever one has the smaller key number, that one is your limiting reactant. So what's the key number for the copper sulfide? All right, what's the key number for the copper oxide? 4.9. because you're dividing 5.6 by 1 or 9.8 by 2. So question, which of these substances, class, is the limiting reactant? The copper oxide. There's your second answer. Copper oxide is the limiting reactant. Does that make sense? Final problem says, okay, if this is the key number we're going to roll with then, we're rolling with the 4.9 because that's the limiting reactant. Is there going to be a little leftover copper sulfide? Sure. We're not going to react all of it. But if 4.9 is the key number, how many moles of copper will be produced? That's the question. How many moles? Well, how do I figure out how many moles, class? Multiply by the key number. We could also multiply that by the other ones, but it's only asking about the copper. So if we multiply, how much do we get?
29.4.
We're going to get 29.4 moles of copper. There's your answer to part C. First of all, did anyone get these answers for A, B, and C? All right, Grace did. All right, those who did not, that's okay. Questions, does it make sense now? Figure out the key number, multiply by the coefficient. How do you get the key number, class? Divide. Moles by coefficient. That gets the key number. Once you know the key number, multiply by the coefficients in question, right? If it only asks about reactants, that's all we got to focus on. If it only asks about copper, that's all we got to focus on. But in theory, could have multiplied the key number by all of them. All right, questions on this? All right, let's take a look at the next one, number 29, and read the original, just the top part of the problem for us, if you would, Nick, nice and loud.
Plants produce glucose through photosynthesis. The overall reaction for this complex process is...
And then they give us this big old long thing. Now the nice thing about the formula, or the equation rather, do you notice, class, that all of the coefficients are what? All the coefficients are the number 6, except for the glucose itself, right? That is a huge blessing, because if they all have the same coefficients, they're all going to have the same number of moles, aren't they? That's going to make my life really, really easy. The mole ratios for all of these would just be 1 to 1, except for, of course, the glucose in question. All right, so part A tells us that we want to produce what, Tyler? 12.1 grams of glucose. There's just one problem. Grams isn't what it's all about, class. It's all about moles. Grams doesn't do anything for me, except I could figure out how many moles if I knew the molar mass. So let's figure this out real quick. 1 mole would be how many grams? Well, hopefully you did this already on your paper, and you said, well, 6 carbon, that's going to be 6 times 12.011. 12 hydrogen, that's 12 times 1.008. 6 oxygen, 6 times 15.999. Add all of those together. How many, on your paper somewhere, you have the molar mass? How many grams are in a mole? And I did it, yes, I have the same number, 180.156. All right, even if you didn't do that, does it make sense? Do we all understand that's what we would do to find molar mass? We've been doing molar mass for a while. So here's the question. Do I have a mole? I'm not even close. Are you kidding me? I'm so far away from a mole, it's ridiculous. I've got like the tiniest 0.0 something of a mole. Does that make sense? But I need to know how many moles. How would I figure out, and it's going to be a tiny number, but how would I figure out how many moles I got, class? Divide 12.1 by the 180.156 it would take to make a mole. And how many moles is that? And it ain't much.
0.067.
0.067, I'm going to do one more sig fig here, 1, blah, 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 but 0.0671 moles. That's practically no moles at all, right? Well, 12 grams is nothing, okay? And it's a pretty large molecule, so it makes sense that we aren't anywhere close to a mole. And here's the question. That's how many moles we have, but I don't really care about the moles. I use the moles to get my what? Key number. It's always about the key number, right? So, if this is the number of moles, what is my key number going to be? How would I find it? Divide it by the coefficient, which is a... so what's my key number? 0.0671, blah, 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 right? That's my key number. Once I know that key number, I can figure out how many moles of everything else I need. Does that make sense? Question? Question? All right. Any questions from anyone on that? So then, part A, how many moles of CO2 are needed? Well, that's right here. How many moles do we need? How do I figure out the number of moles? Class?
Multiply. Take key number 5.
Key number times 6. So how many moles do we need? Take that key number, it should still be on your calculator, multiply by 6. 0.4026, blah, 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 okay? If we're rounding to sig figs, the only number I was given has 3 sig figs in it. What is the problem? You're being a distraction to me, so either get it together or tell me what the issue is. Is there a problem? Okay, get it together, then help me out. I know it's end of the day, we're tired. Hold it together. All right, so going to 3 sig figs, our answer should say
0.403.
0.403 moles. That's our answer to part A. Did anyone have that answer for part A? Okay, does it make sense now? All right, the next thing says, how many grams of H2O are needed? Well, notice it didn't say how many moles are needed, it said how many grams. But in order to know how many grams, we have to know how many moles. How would we figure out the number of moles, class? The key number by coefficient, which not coincidentally is going to give us how many moles again? 0.4026, blah, blah, blah. The number on your calculator, right? That's how many moles of H2O. But it didn't ask how many moles of H2O, it said how many grams of H2O. Well, that's not too bad as long as we know how many grams are in 1 mole. In other words, what is the molar mass? Well, keeping that 0.4026 number in our head, 1 mole. Well, hydrogen's number, 1.008 times 2 would be 2.016. Oxygen's number, 15.999. So let's add the 2.016, the 15.999 to get. All right, 18.015 grams, that's 1 mole. Do I have a mole? We got a little less than a mole, right? I got 0.4-ish moles, correct? How would I figure out how many grams this is? Just multiply the 0.4026 moles by the 18 grams that are in 1 mole, and that tells me how many grams of H2O I need. So, on your calculator, go and multiply those two values. Yes, sir?
So when you're doing all the mole stuff, you don't pay attention to the coefficients? Like,
You use the coefficient to tell you how many moles. Once you know the moles, just multiply. Well, this is how many moles I got. This is how many grams are in a mole. So we just multiply that.
so like when you're finding the 1 mole, you don't use the coefficient?
No. The mole is literally just H2O because it's a mole of H2O. We happen to have 6 of them, but it's just H2O. Okay? 6 relative to the other substances, I should say. We don't actually have 6 H2O molecules. I just have 6 relative to everything else. That's the ratios that they form with each other. All right, so how many grams we need, class? 7.2528. Okay, we did round a little bit. When I did it on my calculator, I kept exact values, so it rounded to 7.26. In our case, though, if we went off these numbers, 7.25 grams, there would be a little bit of lenience there on the rounding, but ideally we would not use rounded values. All right, there's our answer to part B. Does it make sense now? I'm not going to ask if we got it. Does it make sense now? Where that came from. Part C. How many grams of oxygen are formed? Well, can we immediately know how many grams we've got? No, but we can find how many moles we've got. We just have to multiply by the, and what a coincidence. When we multiply 0.0671 by 6 again, we get how many moles? 0.4026 moles. Keeps being the same number of moles because they're all the same coefficient. So that's why it feels redundant. Again, if these numbers were different, it would be a different number of moles. But it's O2. Well, what is O2? 15.999 times 2. That means there's 31.998 grams in 1 mole. Do I have a mole? I have 0.4206 moles. So how many grams do I get out of this reaction? At your seats, just Multiply the 0.4026 moles I've got by the 31.998 grams that would be a mole. How many grams is that going to be? 12.88 rounded 12.9 if we rounded to 3 sig figs. So to get 12.1 grams of glucose, we need 7.25 grams of water. We need whatever it is, we didn't ever find grams, it just asked about moles of CO2. We need 0.403 moles of CO2. We're also going to get 12.9 grams of oxygen produced by it. That's the process we're going to revisit at the end of the review time. We're going to go back and do problems just like these again at the end of the review. For now, go ahead and have just some blank paper we can take some review notes on, and let's practice some things here. First, though, we want to review some terms, and there are not a lot of terms in these two chapters. Did you notice that? It's not a whole lot in the way of terms, but there are some. For instance, what is a symbolic representation of the elements in a compound? Careful, symbolic representation of elements in a compound, not in a reaction. Chemical formula, right? Chemical formula, like H2O, tells you there's 2 hydrogens and an oxygen. That's the chemical formula. Now, specifically, the formula for a molecular compound is called a molecular formula. And the formula for an ionic compound is ionic formula. Okay, those are pretty easy terms, right? Once you remember that the symbolic representation of the elements in a compound is called the chemical formula. Now, in an ionic compound, there's 2 parts. There's a positive part and a negative part. What do we call the positive part of the ionic compound? Cation, and the negative part class is the anion. Now, with the molecular formula, we said the smallest ratio, simplest ratio of the elements in the compound is called the empirical formula. The simplest ratio of elements in a molecular compound is the empirical formula. In an ionic compound, what is the smallest ratio of elements in an ionic compound called? Formula unit. The formula unit. With our different substances, we're constantly asking ourselves about different masses. For instance, the mass of an individual atom is called individual atom. Atomic mass. And that's what's on the periodic table of elements. You will have a copy of that for your test tomorrow. You won't have to keep turning around looking at the poster. You're going to have a copy to keep at your desk. Okay, so atomic mass is each individual atom. That means if you put all those together in a molecule, the total mass of a molecule is called molecular mass. If you were to take the mass of a single formula unit, that would be formula mass. All 3 of those are measured in what unit, class?
Gram.
No. It's represented by the letter U. Remember, it's atomic mass units or unified atomic mass units, just represented by U. Now, we do eventually go to grams with those things. When we go to grams, we're not dealing with molecular mass or formula mass class. We're dealing with, when does it convert to grams? Molar mass. That's what we were just working a second ago, right? With the molar mass, the mass of a mole. Because we can go with grams instead of unified atomic mass units. What is a mole? What is it?
6.022.
Good, 6.022 E23 of anything. Anything that we have, if you have a mole of it, you got that many of it. We call this somebody's number. Whose number, class? Avogadro. Okay, so Avogadro's number, 6.022 E23, that's the number for 1 mole. That's how many of something you would have. And of course, we say the mass of a mole is called molar mass. If we were to find the composition of a compound based on percent of mass represented, we call that what? Percent composition. Composition of a compound based on percent of mass is percent composition. You would simply find how much mass is this, how much mass is that, how much mass is the other. Now divide by the total mass, that gives you your percent composition. We'll look at one of those in a little bit. What term describes the study of the numerical relationships between elements and compounds in a reaction? Stoichiometry. That's a fun one to spell too, right? Stoichiometry. Okay, so stoichiometry, there's an O-I and an I-O in it. Just great fun to spell. Stoichiometry. Also a great word for hangman. It just makes you look like a total nerd if you use it, so I don't really recommend it. But anyway, stoichiometry. Numerical relationship between elements and compounds as they react. Obviously, the collisions between atoms and molecules as two substances come together, the changes that are caused by those collisions is called a chemical reaction. The symbolic representation of a chemical reaction is called a chemical equation. So the formula is like H2O or C6H12O6. That's chemical formula. The chemical equation shows this plus this yields this plus that. In a chemical equation, what's on the right-hand side, class? The right-hand side is the products, and then on the left-hand side would be the reactants. That arrow is red what? Yields. And if there's a triangle above it, it means we have heat added. The reason the numbers work, the reason stoichiometry works at all, is because of the law of conservation of mass. The total masses on one side have to equal the total masses on the other. Or the way we started by thinking about it was simply the number of atoms of every substance has to stay constant. However many atoms of this you have on that side equals the number of atoms you have there. And when the number of atoms of every element match on each side, we have an equation that is said to be balanced. And obviously we did quite a bit of practice with balancing chemical equations. If you've done your extra credit, there were a bunch of equations for you to balance on that handout. In the chemical equation, there are different, we may be given different amounts of various reactions. In a perfect world, the amounts of the various reactants would cause them to each fully react with each other. But in real life, probably one of those reactants will run out before the others. The reactant that determines how much product can be produced, because it runs out first, is called the limiting reactant. The limiting reactant. As far as just pure terms, that's about all we've got. But there are a lot of other things that are memorized things, kind of like terms we need to know. For instance, there are a bunch of prefixes we need to know. For instance, what prefix means to? Di. 3, 4, tetra. 5, penta. 6, hexa. And from there on, we didn't use the rest of them very much, but especially 2 through 6 we used quite a bit. We use those prefixes in naming molecular compounds. For instance, I'm going to make up something that probably doesn't exist. But if I had something like, let's go with this. CO3Fe4. I don't think this exists. If I'm wrong, I'll be shocked. Okay? But if we were naming this molecular compound, we would use the prefix tri, and then we know that CO is cobalt. We memorized that going back to the last test. 4 is, and I might have made a terrible mistake in choosing this next one, because Fe is iron, but our ending is supposed to be I, so I'm pretty sure we would never end with iron, okay? But in theory, iron-ide, okay? That's not usually the case, right? But let's suppose it had been N. That might make it a little easier. Tetra, how would we say nitrogen, but it's at the end? Tetra, nitride. Okay, that one actually sounds a little bit more like it. Okay, so tricobalt tetranitride. Okay, we remember doing this? If you know your prefixes and you remember the "ide" ending, you should be good because they won't be weird to be like iron. I promise they won't be that weird on the test. That's what happens when I make them up off the top of my head. With ionic compounds, how do we name those? Well, we simply name the cation and then we name the anion. Most of our anions end with what? If they're just monoatomic, they just end with I, already on their own. But if they have oxygen in them, it's not "ide" at the end, class, it is "ate" at the end. And we simply name them that way. So for instance, if we had, making this up, something like this. Well, we know that Na, class, is sodium. So we simply state the sodium, no weird prefix needed. And then PO4, well, we know P, class, would be Phosphorus. And if it was just P, it'd be phosphide, right? But PO4 tells me not phosphide, but phosphate. Sodium phosphate. Okay? To remember doing that. All right. If, for some reason, there are water molecules mixed into the crystalline structure, we would have this notation at the end. Raised dot, then H2O. That means there's water in the crystal. What do we call any substance with water in the crystal? Usually an ionic compound. That's if something's dissolved in water, it's an aqueous solution. But what do we call a crystal, an ionic crystal usually, that has water molecules mixed in? A hydrate. That actually would be a term to maybe write down in your notes, a hydrate. And of course, if we had like a 5 in front of it, we would indicate the number of water molecules mixed per formula unit with a prefix. So in this case, we would say pentahydrate. So sodium phosphate, pentahydrate. There very possibly is actually such a thing. I'm not sure if there is, but there might be. All right, questions on that? Okay, so make sure you review. If you felt a little iffy on it, go back and study. How do we name these? This was the very beginning of chapter 3, so it goes way back in our notes. But naming molecular compounds and naming ionic compounds. We talked about different types of reactions, and y'all did fantastic. I think everybody in the class made a perfect 100 on the quiz over the different types of reactions. But which type of reaction has a single element that changes what it's bonded with? A single element changes what it's bonded with. You have 2 substances, you still have 2, but one element trades partners. Single displacement. What if you've got a single substance breaking down into 2 or more simpler substances? Decomposition. What if you've got 2 ionic compounds and they trade anions or they trade cations? Double displacement reaction. And then if you have 2 individual substances joining up to form a new, more complex substance, that's a combination reaction. That's also kind of like terms, but not entirely terms I wanted to review. The rest of the way, let's review some math. So let's see if I can get the mouse working here. All right, so several problems for you to work, and let me get this aimed up here so Olivia can see. At your seats, use the back cover of your book to give you the numbers that you're going to need, but there are several masses I need you to find. Starting with the formula mass of calcium nitrate. Find the formula mass of calcium nitrate. And I'm going to want to turn to my back cover because I don't have these memorized either. Formula mass of calcium nitrate. Once you got the formula mass, move on to the molecular mass. And yes, Olivia, we'll show all the answers here in just a minute. For now, just keep working through these. If we're going too fast, you can pause the video. I don't think I'm going too fast, though. So once you've got the formula mass of calcium nitrate, I think that's butane, if I remember right. Tetracarbon octahydride. Finding the molecular mass. And then finally the molar mass of sulfur hexafluoride. The molar mass of sulfur hexafluoride. Yes, sir. Remember, so a great question. I was actually about to bring that up. Anytime you find molar mass, you're doing the exact same process. But what unit do you use for molar mass, class? Grams. What unit do you use for formula mass and molecular mass? The U, the unified atomic mass unit. So you're going to use U on your first two answers, but molar mass, you're going to do the exact same steps. Don't change anything. Just put G instead of U. Once you've got those three answers, you're going to want to refer back to your calcium nitrite or nitrate answer and be able to find percent composition, but you've already got the numbers that you need for it. So check your first three answers. Make sure you're good on problems 1 through 3. If you've got the formula mass correct, molecular mass correct, and molar mass correct, you're ready to go on to the last problem, which is percent composition. If your first answer is wrong, that's going to mess up your answers for the next one anyway. So, but you'll use the numbers from up here to find your percent composition. How many good on the first 3? You're good on the first 3. All right, so all of you go into percent composition. Let me show the answers to Olivia. Olivia, you're going to want to pause once you see those answers. Pause the video. All right, so all of us finding percent composition. Any questions at all on the first 3? We should be good. I mean, this is stuff we've been doing for forever, so I figured we were good, but did want to make sure we reviewed it. Don't want to assume my way to a bad score for you tomorrow. Nick's good to go on percent composition. Alright. Again, on the test tomorrow, I'll make sure to tell you what I want things rounded to for now. What we did on the quiz when this came up was we did 2 decimal places into percent, so that's what I did here with these answers. I'm going to show this on the board here for Olivia. Alright. Questions on how to do percent composition. It's been a couple weeks. It's not real hard, just take the piece, divide by the whole, the piece, divide by the whole, the piece, divide by the whole. Obviously, that's assuming you've already found either molecular mass, formula mass, or molar mass. Questions? Feel pretty good about that? All right, very quickly then, let's move on to, and get my mouse working here. This is similar to the first homework problem. Ammonia reacts with oxygen to produce nitrogen and steam, and we see the formula there. Okay, go ahead and copy just the equation, rather, not the formula, the equation. Copy the equation on your paper. Copy that chemical equation on your paper. And I'm going to skip some of the notations because I'm lazy. So once you got that equation copied down, we are given in the first part of the problem that we are starting with 5.5 moles of ammonia and 4.5 moles of oxygen. And the question is, which one's the limiting reactant? To figure out limiting reactant, class, we have to know the key numbers. How do we find key numbers? Divide the moles by the coefficient. Okay? So let's divide the moles by coefficient. Let's figure out what the two key numbers would be. Let's figure out what the two key numbers would be. Did you get these two key numbers? And it's not hard math as long as you know what you're doing. Are we all good on the key numbers? Okay, so answer the question, class. Which one, ammonia or oxygen, which one's the limiting reactant? Ammonia. That's the limiting reactant. So, when it says in the next part of the question, based on these given amounts, how many moles of N2 and H2O can be produced? Well, which number are we basing everything off of, class? The 1.375. That's our number. Notice it asks how many moles. That is happy. Because when it asks for moles, it's silly easy to find the number of moles. How do we find the number of moles of each of the products? The key number by coefficient. The 1.375 by 2, 1.375 by 6, boom, you've got how many moles are produced. Really easy problem. So how many moles do we get of nitrogen? How many moles of water? How many sig figs are we allowed in the problem? Looking at the original problem here, the only actual numbers I see are the 5.50 and the 4.50 moles. So that tells me 3 sig figs, because the 0 is significant. So both answers already happen to have the right number of sig figs. It may not be that beautiful tomorrow. So I wanted to make sure to point that out to you. Okay? So that's what you're basing your sig figs on, are not the numbers within the equation, like these subscripts, those are going to be integers, but basing it off of any other given numbers. Questions on this problem? When it asks for moles, that's happy. When it talks about grams, that's painful. Let's finish with our painful problem. Aluminum metal reacts with oxygen gas to produce aluminum oxide. Go ahead and copy the equation on your paper. Again, my lazy self is going to leave off some notations because they don't actually affect the work, they're just there for explanation. Notice they talk about aluminum oxide and we need, it says, 244 grams. Do we divide that by 2? No, we divide moles. We divide moles by coefficient to get key number. I don't know how many moles. What are we going to have to do? Remember just on the last slide, 2 slides ago, we found molar mass. We need to know the molar mass. So we need to figure out how many grams are in 1 mole. So back to your periodic table. How many grams are in a mole? Well, let's see. Aluminum's number is 26.982, but we've got 2 of them. Again, don't factor in the 2. You're looking just at the Al2O3. Don't let the coefficient throw you off for now. We're talking about this substance. There happen to be 2 of them in ratio to the others, but this is the substance. So we're going to have the 982 times 2, and then 15.999 times 3. Let's get what that gives us. Hold on, slow. All right. Whew, that's a lot of grams in 1 mole, class. All right? Do we have the same answer? 101.961? Do we need a full mole class? In fact, we need more than 2 full moles, don't we? So we need 244 grams. I don't care about that. I need to know we need how many moles. Again, it's going to be a little bit more than 2. How do we figure out how many moles we need, class? Good. 244 divided by the 101.961. And I knew it was going to be over 2. In this case, it comes to what? 2.393. That's how many moles we need. You take the 244 grams that we need, but it takes 101.961 grams to make a single mole. So divide the grams we need by how many grams are in 1 mole, and that'll tell you how many moles we've got. 2.393 moles. We all did on the 2.393. Now, once you know the moles, and of course you know your coefficient number, what do I do with them to get my key number, class?
Divide.
You divide. At your seats, find what your key number is. What is our key number for the whole problem? All right, that's our key number, 1.1965. What do I do with the key number, class? Multiply it by all the coefficients. Now, in this case, looking back at the original problem, do I actually care about all the coefficients? The only thing it asks for is how many grams of aluminum. So I really actually only need to worry about aluminum. I could do it for everything, but I'm lazy. Why would I do that? So I'm just going to come to the aluminum, and if I know my key number is 1.1965, multiply that by 4, that tells me how many moles of aluminum we need. Which I need to do that too, don't I? All right, how many moles do we need? 4.786 moles needed. Stay with me. Is that what it asked? Did the problem say how many moles of aluminum are needed, class? No, it said how many grams. So guess what we've got to do? We got to convert to grams. And how do we do that? By knowing what 1 mole of aluminum is. How many grams are in 1 mole? Fortunately, this one's easy. How many grams are in a mole of aluminum?
6.9.
Yeah, it's monoatomic. It's just aluminum, right? So there's no subscripts, there's no multiple stuff. So it's just straight off the periodic table. That's how many grams are in 1 mole. How many moles do we need, class? 4.76, almost 5 moles, and every mole has about 27 grams in it. So how would we figure out the total number of grams of aluminum needed? Just multiply. Take the 4.786, multiply by the 26.982, and how many? This is where we have to round to sig figs, and it's going to be 3 sig figs. All right. So 129.13, blah, 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 but we're going to round to 3 sig figs and say 129 grams of aluminum are needed in order to react with oxygen to produce 244 grams of aluminum oxide. Does it make a little bit more sense now? We looked at it yesterday, did not get as much practice as I wanted. Practiced it for homework, struggled. Now we've gone over it again. Do we see the back and forth between the grams and the moles? Now, on the test tomorrow, you'll have a little bit more time. If you're struggling with the conversion, use dimensional analysis. What do I have? Put it over 1. Take the mole-gram relationship and make a fraction. Put either grams on top or moles on top, depending on what you want to cancel. That'll give it to you. Now, obviously, I recorded this for Olivia, but you all can benefit from it as well. It'll be up on the YouTube channel, so find an old video that got emailed to you and click on it and go to the YouTube channel. It'll get you there. I guess I could email the link to everybody, actually. That would be just as efficient. I'll just do that. If I'm going to email it to her, I'll just email it to everybody if you want to watch it. Just a reminder, this wasn't planned this way because the test was supposed to be today, and it had to get pushed back because we were not able to get as quick as I wanted. But anyway, just a reminder, our STEM background due tomorrow, 2 copies, and the grade form. So bring your STEM book with you because it has the grade form in it. 2 copies, including bib page. One's for the judges, I won't touch that one. One's for me, I'm marking all over that one. Hopefully not too much marking.
Chapter 3 and 4.
Chapters 3 and 4, yep, for the test tomorrow. All right, have a wonderful rest of your day. You are dismissed.